Hi, so today we're going to be talking about the direct and indirect pathways of the basal ganglia. As I start, I want to make a disclaimer. First, that I am not a medical doctor or a biologist. I'm an engineer and a scientist trying to make sense of these pathways and hopefully help others who are starting off. So this is just an introduction. Secondly, these pathways are very, very complex, and I have oversimplified it. There are different hypotheses. I have kind of picked things and simplified it in a way for a beginner to understand. Right. So as we start, if we take the brain and get a coronal slice and zoom in, you should see something like this. And what I have shown in these colors are the basal ganglia. So basically, the basal ganglia coordinates movement. It's basically used for movement modulation. And there are two major pathways, that's direct and indirect, that initiates and terminates movement. So before we go to the pathways, let's talk about the anatomy of the basal ganglia. So first, we have the caudate and the putamen. These are groups of nuclei that are shaped in this way, and they're separated by the fiber tract. So you have the internal capsule here. These together make up the striatum of the basal ganglia. This is the input to the basal ganglia. Next, we have the globus pallidus shown in pink. You have the external segment and the internal segment. Fourth, we have the subthalamic nucleus shown in light green. I've put the capital T here to help with the notation. And finally, you have the substantia nigra, which is kind of the black substance. That's where the name comes from, because of the darker color. So to summarize, we have 5 parts of the basal ganglia: the caudate, the putamen, making up the striatum, the globus pallidus, external and internal, the subthalamic nucleus, and the substantia nigra. The substantia nigra is further divided into 2 parts, the pars reticulata and the pars compacta. So the basal ganglia receives information from the cortex, processes it, and gives the output to the thalamus. So we have the thalamus over here, which is kind of the relay of this whole movement pathway. Now think of it as the gate that activates the motor cortex. So the basal ganglia receives input from the motor cortex, processes it, gives the output to the thalamus, which in turn will activate or deactivate the motor cortex. Right. So I'm going to simplify the anatomy a little bit. I'm going to take out the caudate and draw it like this to help a bit with the explanation. So try to keep this in your mind as we go along, and let me redraw this. And when I redraw this, I'm going to expand this so that I can show you the different parts. So this is that slice. This is where I said, kind of keep it in mind. So we have the motor cortex here. I know this is ugly. We have the striatum, globus pallidus external and internal, the subthalamic nucleus and the substantia nigra. And we have the thalamus. So I'm going to expand it like this and draw. And I have put colors now to help you with this. So we have, we have the motor cortex up here. Then we have the striatum. Even though I've only drawn 1 nuclei, keep in mind, this is for simplicity. We have the globus pallidus internal and external. We have the substantia nigra and the subthalamic nucleus. And then finally, the gatekeeper, which is kind of the relay thalamus. So in normal conditions, we have an inhibitory connection from the GPI to the thalamus. So the point of the thalamus, if you remember, is to activate the motor cortex. But because the GPI is having an inhibitory connection to the thalamus, this is usually not activated. So when we want to start walking, what we want to do is to inactivate this in order for the motor cortex to be activated. Kind of think of it like that. So what we're going to do is, or what happens rather, is the motor cortex has an excitatory connection to the striatum, asking, okay, now I want to move. So what the striatum does is it has a projection to the GPI, which is inhibitory. So in other words, the activity of the GPI is inhibited, which means this connection is inhibited. The activity of the thalamus is going to be increased. There's an inhibition of the inhibition, like a double negative. So then we have activity of the motor cortex. This is the direct pathway. So think of the direct pathway as initiating movement. Right? Now, in this case, if you see the green arrow, this is always excitatory, at least in this slide, and it's glutamate. If you see the red, in this case, it's inhibitory, and it's GABA. These are the neurotransmitters. Okay, so now we go to the indirect pathway. In the indirect pathway, the usual connection, there is a connection from the GPE to the STN, which is usually inhibitory, but the connection from the STN to the GPI is excitatory. So what we want to do is to inhibit this inhibition. In other words, we want to inhibit the inhibition from the GPE to the STN so that this will be excited, so that this will be inhibited and the activity of the motor cortex will be reduced. So let's see how we're going to do that. Right. So it starts off pretty much the same way. You have the motor cortex projecting excitatory connections, exciting the striatum. Then from the striatum, in the indirect pathway, we have an inhibition of the GPE. So when the GPE is inhibited, the activity of the GPE is inhibited, that means it inhibits this connection. So when the inhibition is inhibited, the STN can excite the GPE. So when the GPI, and when the GPI is excited, the GPI inhibits the thalamus and whatever that was happening. So if you were walking, the walking slows down and you can come to a stop. And so this is the indirect pathway which terminates movement. Right. So if you remember, I said I have oversimplified. For example, I have removed the caudate completely from this equation. In addition, we usually have the substantia nigra, the pars reticulata, and pars compacta, which I have not talked about at all. This was not involved in our conversation at all. This diagram will get a little bit overcrowded if I start talking about all of that. So I'm going to draw a block diagram to explain the same thing. This is your basal ganglia. Your striatum made up of the putamen and the caudate nuclei, which is the input to the basal ganglia. You have your globus pallidus, internal and external. You have the subthalamic nucleus and the substantia nigra, pars reticulata, and pars compacta. Then we also have the motor cortex, made up of all of this, the primary motor cortex, premotor cortex, somatary, all of that. And then you have the thalamus. Right. Now I'm going to show you the direct pathway. So in the direct pathway, please keep in mind that when there's an arrow coming in here, it's activating or deactivating both the GPI and the SNR. So there are projections from the striatum to both of these, but we are only going to show it with one arrow. When there are arrows going out, or there's one arrow going out, keep in mind that it's going out. There are projections going out from both the GPI and the SNR. Okay, so as we said, the usual case, the thalamus activity is deactivated or inhibited. And so therefore, the motor cortex is not moving. But let's see how movement is initiated. The motor cortex sends a signal, excitatory signal to the striatum, which inhibits the activity of the GPI and the SNR, which in turn inhibits the inhibitory activity of the thalamus, and therefore the thalamus can excite the motor cortex. So this is what we call the direct pathway, or how movement is initiated. Next, I'm just going to put this up here to help you remember this. So you have the motor cortex, striatum, the simple I and R refer to the GPI and SNR, and T for thalamus. So the first and the last are excitatory, and the middle letters are inhibitory. Hopefully this will help with the memorization. Right, next we come to the indirect pathway. Now this is where the GPE and the STN come in. Here, again, the motor cortex. Okay, before the motor cortex, I talked about how the usual connection from the GPE to the STN is an inhibitory connection. And what we want to do here in activating this pathway is to inhibit this inhibition. So, motor cortex gives the excitatory signal to the striatum, which in turn inhibits the GPE activity, which in turn inhibits the inhibition of this, which in turn leaves the STN free to excite both the GPI and the SNR, which has an inhibitory connection to the thalamus, which, because now this is inhibited, now the activity of the thalamus is reduced. And so if you were walking, this can stop the movement. So what we say is the indirect pathway terminates movement. And to remember it, I have put it up here. So the beginning and the end is the same. What we've added is, oh, I forgot the R here. What we've added is the E and the N. E for GPE and N for STN. So here, now I have added the R. So here is a picture of both the direct and indirect pathways of the basal ganglia. Right. Next, now we have the substantia nigra pars compacta, which we haven't spoken about. We've spoken about initiating movement and terminating movement. As I said, I'm oversimplifying this to make sense of this word. What happens when you want to continue movement? So there are dopaminergic projections from the SNC to the striatum. So the striatum has both D1 receptors and D2 receptors that uptake dopamine. So for the direct pathway, so keep in mind now the direct pathway is a pathway that says, yes, you need to start walking. So the SNC excites this pathway. In other words, it excites the movement, so you keep moving. At the same time, it inhibits the indirect pathway, which is saying to stop the movement. So if you're inhibiting the stopping, that means you're continuing movement. So there's no problem. This is the normal case, right? All of the previous connections, if it was green, was excitatory and glutaminergic. If it was red, it was inhibitory and GABAergic. But these two connections here, again, the green is still excitatory and red is inhibitory, but these two connections are dopaminergic. This is a normal case when we're walking for healthy adults or healthy people. But when it comes to Parkinson, I'm just going to introduce this concept here. What happens is that the dopamine is less. So the SNC activity is reduced, or there's no dopamine coming. So when you're walking, this path starts the movement, but the connection that says keep moving is not there. The indirect pathway, which says stop movement, is not inhibited. So the direct pathway says stop movement, indirect pathway says stop movement. So you have a problem, and this results in the shuffling. And the treatment for Parkinson's, or the pharmacological treatment for Parkinson's, is levodopa, which increases the dopamine of the brain. So that is how the direct and indirect pathways work. And I want to reiterate that I have oversimplified this. And hopefully very soon I'll do another video talking about Parkinson and also what deep brain stimulation does in Parkinson. Thank you very much.